In this episode, we're going to take a careful step past the basic idea of encryption and into a few modern concepts that sound intimidating at first, but become very manageable when you tie them to simple goals. Cryptography is ultimately about creating trust in an untrusted world, and that trust usually comes down to three needs: keeping information secret, proving it hasn't been changed, and confirming who you're talking to. As systems grew more connected and attackers got more capable, cryptography had to evolve so it could protect data not just on a hard drive, but while it moves across networks and while it is processed by services you may not fully control. The terms in today's title point to that evolution, because each one solves a different modern problem that older approaches handled poorly or not at all. By the end, you should be able to explain what post-quantum cryptography, PQC, forward secrecy, authenticated encryption with associated data, AEAD, and homomorphic encryption are trying to achieve, and why they matter even if you never write a line of cryptographic code. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Before diving into those advanced concepts, it helps to refresh the simplest picture of what cryptography is doing in a system, because advanced ideas are usually just careful answers to basic failures. When you encrypt data, you're trying to keep it confidential so that someone who intercepts it cannot read it. When you add integrity, you're trying to ensure that if someone alters the data, the change will be detected. When you add authentication, you're trying to confirm that the party on the other end is the one you intended, not an impersonator. In real systems, these goals often overlap, and that overlap is where confusion begins for beginners, because it can look like one feature should do everything. A key mindset is that cryptography is not one magic feature, but a set of tools that must be combined correctly to create the security property you want. Another important point is that cryptography usually depends on keys, and the security of the system often collapses when keys are stolen, reused incorrectly, or managed poorly. Once you hold on to that, advanced cryptography becomes easier to understand as methods for reducing key risk and reducing the ways attackers can exploit mistakes. Another foundational idea that supports this whole discussion is the difference between algorithms and keys, because beginners often treat the algorithm name like it is the secret. The algorithm is the method, the math recipe that everyone can know, while the key is the secret input that makes the output unpredictable to outsiders. This is an important principle because strong cryptography assumes the attacker knows the algorithm, and the security comes from the attacker not knowing the key. When people misunderstand this, they may focus on hiding details rather than protecting key material, which is backwards. Advanced cryptography often focuses on making it harder for attackers to get useful keys, making it less damaging if a key is exposed, and making it easier to prove that two parties share the right secrets without revealing them. It also focuses on making cryptography safer to use by reducing the number of ways developers can accidentally combine pieces in an insecure order. So as we discuss PQC, forward secrecy, AEAD, and homomorphic encryption, keep asking one steady question. What key or trust problem is this idea trying to reduce, and what weakness in older approaches is it addressing? Post-quantum cryptography, PQC, starts with a future-looking concern that has become very practical to plan for. What happens if large-scale quantum computers can break some of the public key cryptography methods we rely on today? Many systems use public key techniques for things like key exchange and digital signatures, which are essential for secure web browsing, software updates, and identity verification. The worry is that certain mathematical problems that are hard for classic computers may become much easier for quantum computers, making some widely used public key approaches unsafe. Beginners sometimes hear this and assume quantum computers will instantly break all encryption, but that is not the full story. Most symmetric encryption, which is the kind where both sides share the same secret key, is generally affected differently and can often be strengthened by choosing larger key sizes. The bigger concern is that public key systems could be disrupted in ways that break trust at the foundation, such as allowing attackers to impersonate servers or forge signatures. PQC is the effort to design and adopt new cryptographic methods that remain strong even if quantum computers become capable enough to threaten current public key systems. What makes PQC especially important in security planning is that cryptographic transitions take a long time, and attackers can take advantage of time in a way that feels counterintuitive. One common threat model is sometimes described as harvest now, decrypt later, where attackers collect encrypted traffic today and store it, hoping to decrypt it in the future when the math becomes easier. That means data with long-term sensitivity, such as health records, intellectual property, and government information, could be at risk even if it is encrypted strongly today, if the encryption depends on algorithms that may become breakable later. Another reason PQC takes time is that it is not just a swap of one algorithm name for another. It often changes key sizes, performance characteristics, and compatibility across devices and services. Beginners sometimes assume organizations can wait until the day quantum computing arrives, but by then, the transition pressure would be enormous and risky. A safer mindset is to treat PQC as a planned migration, where systems are made flexible enough to support new algorithms without rebuilding everything. In that sense, learning PQC is learning how defenders manage long-horizon risk responsibly. At a high level, PQC includes new families of cryptographic techniques designed around mathematical problems that are believed to resist known quantum attacks. You do not need to memorize the families to understand the security point, which is that diversity in mathematical foundations reduces the chance that one breakthrough breaks everything. You can also think of PQC adoption as requiring two major capabilities: new ways to exchange keys safely and new ways to sign and verify trust relationships. This matters because secure connections often rely on exchanging a shared secret to encrypt the session, and software distribution often relies on signatures to prove updates are authentic. Another beginner misunderstanding is thinking that switching to PQC is purely a confidentiality decision, when integrity and authenticity are often the more urgent concerns. If signatures become forgeable, attackers could deliver fake updates that look real, which is catastrophic. So PQC is not just about hiding secrets. It is about preserving the ability to prove identity and integrity in a future where current assumptions may fail. The deeper lesson is that cryptography protects systems over time, and time is an attacker's ally unless you plan ahead. Forward secrecy is another concept that is easier than it sounds once you link it to a common failure mode. What happens if a long-term key is stolen? In older designs, a server might use the same private key to help establish secure sessions over a long period of time. If that long-term private key is compromised, an attacker might be able to decrypt past recorded sessions or impersonate the server going forward, depending on how the system was designed. Forward secrecy aims to limit that damage by ensuring that even if long-term keys are stolen later, past session keys remain protected. This is a huge improvement in real-world security because it assumes compromise can happen, and it tries to prevent compromise from rewriting history. Beginners sometimes hear the word secrecy and assume it means sessions are invisible or anonymous, but that is not the point. The point is damage containment across time, meaning a compromise today should not automatically reveal yesterday. When you understand forward secrecy as time-based blast radius reduction, it becomes a very practical and modern security goal. To understand how forward secrecy works at a high level, focus on the idea of session keys that are created fresh for each connection and are not stored long-term. A secure connection, such as one protected by Transport Layer Security, TLS, uses cryptography to establish a shared secret and then uses that secret to encrypt the data for that session. With forward secrecy, the secret that protects the session is derived from ephemeral values, meaning values that exist only for that session and are discarded afterward. A common way to do this involves Diffie-Hellman, DH, style key exchange where each side contributes a temporary secret and they combine those secrets to create a shared key. The important beginner insight is that the long-term identity key can still be used to authenticate the parties, but it is not the key that directly encrypts the session data. That separation is what reduces damage. Even if the identity key is later stolen, the ephemeral session secrets that were used to create past session keys are gone. So forward secrecy is not a separate encryption algorithm. It is a design property created by how keys are negotiated and managed. AEAD is a concept that tackles another real problem. Encryption alone does not guarantee that data hasn't been altered, and combining encryption and integrity checks incorrectly can create vulnerabilities. Authenticated encryption with associated data, AEAD, is a type of encryption approach that provides confidentiality and integrity together, and it also allows certain data to remain unencrypted while still being protected for integrity. That unencrypted but integrity-protected part is the associated data, which might include headers or metadata that must be readable for routing or processing, but should not be editable without detection. Beginners often assume that if data is encrypted, it cannot be tampered with, but encryption by itself can sometimes allow changes that create meaningful effects, especially when systems respond differently to modified ciphertext. AEAD is designed to reduce that risk by making the integrity check a built-in part of the encryption operation, so the receiver can verify the message is authentic before trusting the plaintext. This matters because attackers frequently exploit systems that accept modified data and behave in revealing or dangerous ways. AEAD is about making the safe way the default way, reducing the chance that developers accidentally build a system that is confidential but not trustworthy. The reason AEAD is considered advanced is not because the idea is complex, but because it reflects lessons learned from decades of real-world cryptographic mistakes. In older designs, developers sometimes encrypted data and then separately created a message authentication code, but the order and details matter, and small errors can lead to big vulnerabilities. If a system checks integrity too late or reveals different error behavior depending on what failed, attackers can sometimes learn information they shouldn't. AEAD helps prevent those mistakes by packaging the confidentiality and integrity operations into one combined scheme with clearer safety properties. Another beginner misunderstanding is thinking that integrity is only important for stopping attackers from changing what you read, when it is also important for stopping attackers from changing what the system does. A small change in a command message, a transaction, or an access token can have massive impact even if the attacker can't read the message content. AEAD aims to ensure that if anything about the protected message is altered, the receiver will detect it and reject it without exposing extra hints. In practice, AEAD is a major reason modern secure protocols are harder to break than earlier generations. Homomorphic encryption is one of the most mind-bending concepts on this list, but the core idea can be expressed simply. It allows computation on encrypted data without decrypting it first. Normally, if you want to run a calculation, search, or analysis, you decrypt the data, process it, and then possibly encrypt the result again. That workflow exposes plaintext during processing, which can be risky if the processing happens in a place you don't fully trust, like a shared cloud environment or a third-party service. Homomorphic encryption changes the story by allowing certain operations to be performed directly on ciphertext, producing an encrypted result that, when decrypted, matches what you would have gotten if you had processed the plaintext. Beginners sometimes hear this and assume it means you can do anything you want on encrypted data at normal speed, but that's the misunderstanding to correct. Homomorphic encryption is powerful, but it is computationally expensive and often limited in what operations are practical in real systems today. Still, it is a major concept because it offers a way to reduce the trust you must place in the environment that processes your data. It is an example of cryptography being used to reduce the need for organizational trust, not just to hide data in transit. Understanding where homomorphic encryption matters is easier when you connect it to modern data realities, where organizations want to analyze sensitive data while keeping it protected from insiders, service providers, or compromised systems. Imagine wanting to compute statistics on private records without exposing individual entries to the system doing the computation. Homomorphic encryption aims to make that possible by ensuring the system can perform the math while never seeing the raw values. The trade-off is that you pay for that privacy with complexity and performance cost, which is why it is often used selectively rather than everywhere. Another practical point for beginners is that homomorphic encryption is not a replacement for access control or good system design, because the keys still matter and the outputs still need to be handled safely. It is also not a way to avoid all trust. because you still must trust the key holders and the correctness of the cryptographic implementation. The deeper value is conceptual. It shows that cryptography can protect data even during processing, which is one of the hardest phases to secure. When you see it that way, you can understand why it appears in discussions about privacy-preserving computing and secure analytics. These advanced concepts connect to each other through a shared theme, reducing the consequences of compromise and reducing how much you must trust the environment. PQC is about reducing future compromise risk from advances in computation, especially around public key foundations. Forward secrecy is about reducing the damage of key compromise over time by ensuring past sessions remain safe. AEAD is about reducing the risk of tampering and unsafe composition by combining confidentiality and integrity correctly. Homomorphic encryption is about reducing exposure during computation by keeping data encrypted even while work is performed. Beginners sometimes treat these as separate buzzwords, but they are all responses to real attacker strategies. Attackers capture traffic and wait, so we plan for PQC and forward secrecy. Attackers modify messages to trigger dangerous behavior or leak information, so we use AEAD. Attackers target places where data is processed in plaintext, so we explore techniques like homomorphic encryption. The more you can frame cryptography as a set of defensive answers to attacker behavior, the more it feels like a practical discipline rather than abstract math. A final set of beginner-friendly clarifications can help keep you from building false confidence around any one term. PQC does not automatically make a system secure if keys are mishandled, because key theft still defeats strong math. Forward secrecy does not mean attackers can't see traffic. It means recorded traffic is less useful if long-term keys are compromised later. AEAD does not mean messages can never be tampered with. It means tampering is detected reliably and the system is designed to reject altered messages safely. Homomorphic encryption does not mean you can skip security controls elsewhere. It means you can reduce certain exposures during computation, usually at a cost. Another common misconception is that advanced cryptography is only for specialists, when in reality, many of these concepts are embedded in the protocols and services people use every day. Your job as a defender is often to understand what properties you are getting and what assumptions those properties rely on, rather than to invent new cryptography. When you can explain these ideas clearly, you can make better decisions about risk, architecture, and how to prioritize security improvements. To conclude, advanced cryptography is best understood as modern damage control and modern trust engineering, not as mysterious mathematics. PQC is about preparing for a world where some of today's public key assumptions could fail, so long-term confidentiality and signature trust can survive future capabilities. Forward secrecy is about ensuring that even when keys are compromised, the past is harder to recover and the blast radius across time is reduced. AEAD is about protecting both secrecy and integrity together in a safer, more reliable way that reduces common implementation errors and makes tampering far harder to exploit. Homomorphic encryption is about protecting sensitive data even while it is being processed, shrinking the places where plaintext exists, and reducing how much you must trust the processing environment. When you connect each concept to the real problem it solves, you gain a durable understanding that will carry forward even as specific algorithms and products change. The strongest takeaway is that cryptography is not just a lock on a message. It is a set of design properties that shape how systems behave under attack, and these advanced ideas exist because attackers taught us where the old designs broke.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.